Hydrogenation is the addition of hydrogen to a multiple bond. The reaction of hydrogen with an alkene is exothermic, and it's characterized by a negative sign for delta H. Uncatalyzed addition of hydrogen to an alkene, though, although exothermic, is very, very slow, but its rate is increased in the presence of certain metal catalysts, such as finely divided platinum, palladium, rhodium, or nickel. In the presence of those catalysts, the reaction is normally rapid at room temperature, and the alkane is the only product that's obtained. The solvent that's used in catalytic hydrogenation is chosen for its ability to dissolve the alkene. It's typically ethanol, hexane, or acetic acid. The metal catalysts are insoluble in those solvents. Indeed, they're insoluble in almost any solvent. Two phases, the solution and the metal, are present, and the reaction takes place at the interface between them. Reactions involving a substance in one phase with a different substance in the second phase are called heterogeneous reactions. So we say that these are heterogeneous catalyst hydrogenation reactions. The stereochemistry of the reaction is such that there is stereospecificity and stereoselectivity that attend catalytic hydrogenation. You can see that in the example shown in the lower right of this slide, where the hydrogen is added in a syn fashion. The mechanism of the heterogeneous reaction is illustrated in this video. Hydrogen molecules react with the surface of the metal at the catalyst surface. The relatively strong hydrogen-hydrogen sigma bond is broken, and it's replaced by two weak metal hydrogen bonds. In the second step of the mechanism, the alkene reacts with the surface of the metal catalyst, and the pi bond is replaced by two relatively weak metal carbon sigma bonds. A hydrogen atom is transferred from the catalyst surface to one of the carbon atoms, and then a second hydrogen atom is transferred, forming an alkane. The sites on the catalyst surface at which the reaction occurred are free to accept additional hydrogen and alkene molecules, and so the reaction can proceed. So we can think of the whole process as being four fundamental steps. Hydrogen reacting with the catalyst surface. We think of the catalyst as activating the hydrogen. The alkene reacting with the catalyst surface, forming a reactive species. And then hydrogen transfer, sequentially one hydrogen and then a second hydrogen, and at that point the alkane is released from the metal surface, and the metal surface is regenerated so that further catalysis can occur. Experimental support for the syn addition can be found in the hydrogenation of cyclohexene using D2 instead of H2. Spectroscopic analysis confirms that 100% of the product shows that the deuterium is added in a syn fashion. Further evidence of the heterogeneous nature of the reaction comes from the reaction of the molecule shown here at the bottom of the slide. This is alpha-pinene. The structure of alpha-pinene, its bicyclic structure, places a methyl group on one face of the alkene, blocking the interaction of that face of the alkene with the catalyst, and so hydrogen can only be added from the bottom side of this molecule, producing again syn addition. The conditions for hydrogenation of alkynes are similar to those employed for alkenes. In the presence of a finely divided platinum, palladium, nickel, or rhodium, 2 molar equivalents of hydrogen add to the triple bond of an alkyne to yield an alkane. Like the hydrogenation of alkenes, hydrogenation of alkynes is a syn addition. Cis alkenes are the intermediates in the hydrogenation of alkynes to alkanes. You can actually isolate the cis alkene with special hydrogenation catalysts. The most frequently used one is Lindlar catalyst, which is this combination of reagents that we see here. Lead acetate and quinoline partially deactivate or poison the catalyst, making it a poor catalyst for alkene hydrogenation while retaining the ability to catalyze the addition of hydrogen to the triple bond. And so we can get good yields, we can see, of exclusively cis alkenes. A useful alternative to catalytic partial hydrogenation for converting alkynes to alkenes is the reduction by group 1 metals, lithium, sodium, or potassium, in liquid ammonia. The unique feature of metal ammonia reduction is that it converts alkynes to trans alkenes, whereas catalytic hydrogenation yields cis alkenes. Thus, from the same alkyne, one can prepare either cis or trans alkene by choosing the appropriate reaction conditions. The stereochemistry of the metal ammonia reduction of alkynes differs from that of catalytic hydrogenation because of the mechanisms of the two reactions are different. The mechanism of hydrogenation of alkynes is similar to that of catalytic hydrogenation of alkenes. Metal ammonia reduction of alkynes is shown here. As we can see in this video, the mechanism consists of 2 single electron reductions and 2 proton transfers. All right, let's play that one more time and watch what happens. The first step of the mechanism is a single electron reduction of the alkyne to a radical anion, very strong, powerful base, which deprotonates ammonia, the solvent. This leaves a radical that is reduced again by another single electron reduction to an anion, another powerful base, that deprotonates another molecule of ammonia, ultimately giving a trans alkene, the more stable alkene structure. Let's draw out the mechanism of that process. The first step is a single electron reduction from sodium metal. So we're going to donate an electron and break one of the pi bonds. Notice the fishhook arrows here. We need 3 of them. So the pi bond is broken, 1 electron to each carbon, and on one of those carbons the additional electron from sodium goes. So this produces a radical on one carbon and an anion on the other carbon, and the most stable structure for that is a trans arrangement. This species is a powerful Bronsted base and will deprotonate an ammonia molecule, our solvent in the reaction. In this case, we're using full arrowheads because these are electron pair movements, just a Bronsted acid-base reaction. So we add a hydrogen to one of the carbons, and we're still left with a radical. This is then reduced again by another sodium atom, single electron transfer. Oops, I can fix that. There we go. To produce an anion. It's a carbon anion, so it's a very powerful Bronsted base, which deprotonates ammonia. To give our product. In the stereochemistry, the trans stereochemistry of the alkene is established in that first reduction step. So that concludes our material for Chapter 11. It also concludes everything for the semester. So here's the usual list of essential skills. In this chapter, this includes things like predicting the products for hydrogenation, the mechanism of halogenation of alkenes, the mechanism and the products for the reaction of alkenes with halogens in the presence of nucleophilic species, the mechanism of oxymercuration, demercuration, the mechanism of epoxidation and cyclopropanation. There are many other details that you should be aware of, such as the difference in nucleophilic attack on oxiranes under acidic versus basic conditions. You should be able to provide a mechanism and predict the products of ozonolysis with either a reductive or an oxidative workup. You should be able to predict the products of the reaction with manganese and osmium reagents, provide mechanisms and predict products of HX, H2, hydration, and hydroboration and oxidation of alkynes. You should be able to draw a mechanism for tautomerization and rationalize why enols form carbonyls, and describe the conditions that will selectively form either alkanes, cisalkenes, or transalkenes from alkynes. Here's the usual list of practice problems, and you should focus on those as you study.